Hi there, I'm Gareth Davies. I'm projects lead for Holoplot, and thank you for joining us here at our headquarters here in Berlin. Today, what we're going to be looking at? Well, we're going to be doing an introduction to the Holoplot X1 series. And this is going to be the first of a series of webinars looking at the Holoplot X1 series. And we're really excited that you could join today and really kick this off. So what have we been up to? Well, we are recently a multi-award winning product. We come back from Best in Shows at ISE and Infocom, which we're really excited about and really think's a good start to kicking off this product. So here we go, let's go into the slides. So what we're going to be looking at today. So first of all, it's we're going to look at the why. So why do we need a matrix array and the evolution of pro audio? Then the what. So what is the X1 series? The audio modules we're going to look at are the MD96 and the MD80S that kind of make up this series, and we're going to look at more detail around those and the different configurations. And then how does it work? You know, we're going to look at the reproduction engines and the beam types, which is kind of new things to consider when thinking about audio systems, and something we wouldn't have considered with conventional systems at all. So that's something new to look at there. So let's kick this one off. So we're looking at the evolution of pro audio. And that's a quest for directivity control. So what's driven this quest really? Well, over the years, you want to kind of cover large areas, whether that be large festival sites or multi-tier auditoriums, and the ability to control the sound within those venues. And then this improved control of the radiation pattern of the speaker, so to improve intelligibility and reduce unwanted reflections. It's not about having the loudest system, it's about how you control the energy. And obviously at Holoplot now, we've taken that a step further in terms of how we do that. So we look at the diagram here, and we can kind of see from the multi-cell horns in the 1930s straight through to kind of line arrays, which are obviously still used now. And then I guess it's the second part of my career that we actually looked at. So at the start, we've got the sort of live sound engineering side, the music reproduction in terms of these, in terms of the line arrays. Then we look at the bottom, we actually look more at kind of maybe speech reproduction and PAVA systems, and in terms of how the developments work there. And we go from a column loudspeaker, we go through to a digital column array where we actually use DSP to actually control the steering of the system. And then we go to the optimized digital column array, which is when we actually optimize for the coverage. But all of this obviously is only in the vertical axis that we're actually able to control this sound all the way through when we're looking at this. And what do the different kind of beam patterns look like that you're actually able to achieve from these different types of loudspeaker? Well, as we can see on the left-hand side, we have the mechanical steering. And this, is obviously to do with the shape, the number, and the positioning of the cabinets that you actually have in terms of controlling this radiation pattern. And we can see that it's quite a wide pattern. It's a fixed pattern in terms of how we're able to control that. And then we go on to the digital beam steering. Now, with the digital beam steering, you're able to actually manipulate that and actually move that in terms of where you want that energy to be focused on. And we do this by changing the phase of two or more of the loudspeakers that are installed in the column, where the combined sound is then added and cancelled at the required direction to be able to get that level of control. And then the next thing we look at then on the right-hand side is this beam shaping technology. So this is then actually sort of using these optimization algorithms to synthesize the vertical directivity pattern of the array based on the room geometry, which is something that we've never had before really. And that was actually first introduced by Duran Audio in the 1990s. And that's our own Ebbett Start that works here actually kind of pioneered that work and actually deployed those optimization algorithms within Duran's DDA software. So what have we gone from there? So we've taken it to kind of mechanical steering, digital beam steering, then we kind of have this beam shaping and this kind of optimization process. And then we take that one step further. So this is kind of introducing the Holoplot X1 series. Now, as you can see, it looks very different to anything that we showed on that previous diagram. And we believe that this is the evolution of loudspeakers. So it goes from the point source right in the early stages and through to this quest for directivity that we've just talked about, from the line array or the beam steered column to, right up to kind of the optimized digital beam steering. And this we consider to be a new category of sound system with the X1 series. And we call this the matrix array. This is the ability to be able to steer sound in both the horizontal and the vertical axis. And it gives you so much more control than we've ever had previously. And we'll look at that in terms of how those beams work and the coverage areas and the precision that we're able to achieve there in later slides. So we don't refer to these as loudspeakers because they're so smart in the way that they are actually made. We believe that we actually refer to these as modules. And when we build these, obviously the matrix arrays, this matrix configuration, we're able to build the matrix out in both the horizontal and the vertical. And a lot of the time we do that to match the aspect ratio of the room. Or it can be if you have very reflective side walls, for instance, but quite an absorptive rear wall, and actually you want to take all the energy off of those side walls, then you would build the array out wider to be able to get a greater level of control in the horizontal plane to really focus the sound where you want it and not on the reflective surfaces where you don't want it. But we'll look at that more in a little more detail coming up. So what does the X1 series comprise of? Well, it's two modules that we currently have here. So we have the module 96, so-called for the 96 drivers, and we'll look at that configuration in a second, and the module ATS, and again, because of the 80 drivers, as you may have guessed. And you can see on the ATS that actually there are two ports, the two tune ports on either side, and that's because it has an 18-inch iPAL subwoofer in the rear there. So looking at this driver configuration, so it's a multi-layered driver configuration that we're looking at here. And that starts at the front end with the 1.3-inch soft dome tweeter, and as you can see, there's 78 of those within this, and they have waveguides to actually be able to control those radiation patterns from those tweeters. And then there's the 18 5-inch drivers that we have in behind that are ported because they sit in behind the 1.3-inch soft dome tweeters, and they are kind of in a sort of pseudo random configuration. And again, we'll talk about that later in terms of why we do that. So then moving on to the MD-ATS, and the MD-ATS, in terms of the top layer, the configuration is the same. So you still have these 1.3-inch soft dome tweeters, you still have the 5-inch driver, but then sitting in the rear of the unit, you have the 18-inch iPAL subwoofer. So we'll come back to that a little later, but that's the general configuration of both those boxes. So we get asked quite a lot in terms of, what is the max SPL output of these boxes, and here we go. Obviously, this is available on the spec sheets, and it's something that you can have, and we're happy to share with you. So looking on the left-hand side, so we've got the MD96, and we've got, in terms of different bandpass sections to the different layers of the drivers. So in the low frequency, we've got a max SPL of 142 dB. And then on the high frequency, you've got 152 dB. In the MD-ATS, then obviously we pull the sub into play, and we've got 131 max SPL there, and then for the low frequency, 141, and then the high frequency, 151. And you can see that there's a slight reduction in the SPL in the LF and HF for the MD-ATS, and obviously that's due to just the reduction of the number of drivers in that unit. So sort of moving on then in terms of the frequency range and the crossover frequencies we can expect to see from this. So the MD96 is a full range cabinet. A lot of the time we'll only drive it down to maybe 100 hertz, but this can actually be extended. You can have a low frequency extension down to almost down to 70 hertz if required. But obviously that will have a slight reduction in the max SPL when you spread that over a wider frequency range. And then with the MD-ATS, obviously with the integrated subwoofer, we can run that down, as you can see, down to sort of 26 hertz and right up to 20K, because it's got the full range as it is a three-way box. So that's just a quick look at the frequency response of that. Again, if you require that, we can make that available. So what kind of makes all this work? What's the kind of magic that sits in behind this? And this is the electronics package. This is the intelligence that kind of sits behind the unit and actually ensures that all of these drivers work together. So each of the drivers then is individually amplified and DSP processed. There is an FPGA, which is a field programmable gate array that's handling the signal processing. It's a decentralized processing system in that respect. So there's no supercomputer that sits at front of house that's kind of doing all the processing here. Everything is actually done on board of the unit. These boxes can either be Dante or we can have Ravenna, and you'll specify that at the time of purchase, depending on which audio network format you actually want to go with. And then health and performance monitoring. Now, there's a lot of smart features that are on board this box, and monitoring that we can do remotely. So we can access kind of the temperature data of the box. We have built-in microphones to the box that can actually measure the acoustic impedance. So we can look at individual driver health, and then there's a certain level of predictive maintenance we can do in terms of if we think a driver is not performing acoustically as it should do, then at least we can highlight that, or we can switch the unit out. This is really useful, and I suppose there's a slight sort of built-in redundancy there in terms of the amount of drivers that you actually have. If a single driver goes down, then it's not really going to affect the performance of the box, and the box can be re-optimized. But it's worth certainly having that level of predictive maintenance there to ensure that you know how the box is performing. And then there's the IoT capabilities. Now, this is the ability to actually access the system remotely. And this is something that's come in really handy lately, obviously in COVID times, where we've really struggled sometimes to get field engineers out onto site to actually do maintenance of the system. And we're able to access the system remotely, maybe from our headquarters here back in Berlin. And we can update software, we can update firmware, we can do system checks. So when we do actually get an engineer then out onto site, they have a much smaller amount of work to do, and we can reduce the time that they need on site to be able to commission a system. So some very, very useful capabilities there. So now we're going to look at the technology pillars that we actually have within the Holoplot X1 system. So there's two sort of categories here. We have the 3D audio beamforming. So this is our ability to control the sound in both the horizontal and the vertical axis we talked about, and shape these beams in a 3D way. And then we have the Wavefield synthesis functionality. We'll talk about that a little bit later and what that entails. So within the 3D audio beamforming, we have parametric beams and we have coverage beams. Again, we'll cover that in just a second. And then we have what we call virtual sources as part of the Wavefield synthesis functionality, and we'll look at that in some detail in a minute. So first of all, we're going to kick off with parametric beams. Now, what is a parametric beam? So a parametric beam, in terms of the sort of its controllable parameters, are its direction, so the angle that you actually be able to steer the beam at, both the vertical and horizontal, and that's measured in degrees in terms of how we measure that. And then the width of the beam itself, again, both in the vertical and horizontal, so the height or the width of the beam that you're trying to steer. And then we can adjust the performance targets as well. So each of them we can actually look at the EQ, level and delay of each of those beams individually. And all of this can be done in real time. In terms of within the software, we can drag and drop these beams around as we want to and move them around in real time. There's no pre-processing done on these beams in terms of being able to shape them. And per either array or per module, you can have 8 of these parametric beams. So worth thinking about later in terms of how you actually are able to create the sound design and the number of beams you've got available to you to be able to really sort of layering up these different parts of the sound design. So here we go. So when using parametric beams, what can you expect to see from sort of the radiation pattern, I suppose? You know, what are the effects of actually steering the beam? So first of all, I mean, let's look at this diagram. We see the main lobe we talked about in terms of the opening angle of that beam. Again, you measure that in either the vertical or the horizontal. And then you've got the steering angle as well that we can see here, again, looking at that in degrees in terms of how much you are able to steer the beam. And then dependent on that, you're sort of creating a couple of artifacts here. The first one you can see here is the grating lobes. And the grating lobes are determined by the driver spacing. And this is sort of causes sort of a spatial aliasing. To avoid spatial aliasing, the spacing of the driver should be smaller than half the wavelength for the maximum frequency to be controlled. If the distance is greater than half the wavelength, this causes an undersampling of the original audio source, creating these grating lobes. And these grating lobes consist of uncontrolled sort of high frequencies. These are not broadband in the way that the main beam would be. Although they look like this on the diagram, that you can't see what the actual frequency kind of makeup of those lobes are, but these are very much in the high frequency. And then you can see that we've got these small side lobes. Now, in terms of how you steer, you get a certain amount of edge diffraction off the side of the box. And the more extreme the steering angle, sort of the greater the effect of this. Now, obviously, we understand this, and these are sort of key principles of beam steering. Now, the Holoplot X1 was designed to certainly designed to reduce the spatial aliasing by minimizing the spacing between the drivers, but also making a pseudo-random arrangement of the drives as well, so there isn't a specific frequency that is uniformly kind of hit there. So we're actually able to sort of spread that and spread the sort of phase response. And then to mitigate the impact of the side lobes, we deploy side lobe suppression algorithms in the form of gain tapering around the edge of the box. So reducing the level in the drivers to the outside of the box, which again reduces the level of the side lobes that are created when you're actually steering the beams there. Excuse me. Okay, so what we're looking at here, well, this shows how we're able to steer low frequencies. And the frequency you can control is a function of the size of the wavelength you're trying to control. So looking at this, we can see that we have a 3-wide array here, and we've got a 3-high. So that means that you're actually able to sort of control low frequencies the same in the vertical as you are in the horizontal. And the more you expand that out, the greater level of control you will have. So the wider the array is, the lower the frequency that you're able to control. And this is shown in these curves here. These curves are ultimately just physics at the end of the day. And it's interesting because we often have people come up and, when they see an array that we've deployed, they say, okay, so with that array, what frequency can you control to? And they almost think about it as kind of this kind of binary control. You can steer at 400 hertz or you can't steer at 400 hertz. And obviously then looking at these curves, we can see that that's not the case. And actually what it is in terms of what is the beam width that you're able to achieve given the size of the box. So let's have a look at this in a little more detail. Obviously we look from having a 1x1 configuration of an array right up to an 8x8 configuration. And we can see the different colors and the different beams in terms of how you're actually able to get a greater or a smaller minimum beam width in the lower frequencies when you go right up to the 8x8 array. And to kind of show what that looks like, we've kind of added this subwoofer range, I suppose. And even with an 8x8 array that we have here, you're still able to control right down. I mean, still getting the minimum beam width down to kind of 60 degrees, even down to kind of 45 degrees within the subwoofer range. So that gives you an idea of what you're able to control with a given size of array. So moving on to coverage beams. So that's just covered off parametric beams. We're now going to move into coverage beams. Now, what is a coverage beam? Well, a coverage beam can be tailored to any shape audience area by pre-processing these beams in our Holoplot plan software. The beams can be optimized for both homogeneity of coverage and spectral uniformity. There's minimum level loss over distance then, because we optimize that in terms of homogeneity right across the audience area. You get none of this sort of hot spotting that you would off a point source when you're very, very close to the sound. You really reduce that down. And this means that every audience member gets the same experience. In terms of how many of these beams we can create per array, we said that it was 8 with the parametric beams, and for the coverage beams, because they require this level of pre-processing, and we can create 4 of these coverage arrays, the coverage zones per array or per module. So then how do we set this up? And why do we set it up like this, I suppose? So we have sort of 2 types of zones here that we've created. So we have an audience zone. So this is obviously the zone that you want all of your energy to be focused on. This is where you want the even coverage right across those audience zones, and you want that spectral uniformity as well. So you want that sort of constant frequency response across that area. But then we also have avoidance zones, areas that we don't want to hit. And we specifically put those in to ensure that we reduce the amount of energy that will actually spill onto these zones. So as we can see in this particular diagram, we've got the rear walls of the venue here, and we've also got the stage. And obviously the stage, to improve the sort of level of gain before feedback level, then you want to reduce the amount of spill onto stage as much as you can. And then we have the back walls here, that if they are a fairly reflective surface, then you can get this slapback delay, which can really impact the performers on stage and ultimately drive down the intelligibility of the sound within the venue. So there's very sort of useful tools that we can do there. And some of the recent theatre designs we've been doing here at Holoplot, we've actually looked at kind of avoidance areas on balcony fronts as well, which is a common problem, certainly in a lot of the older theatres. They have very reflective balcony fronts, and that causes this slap back down towards the stage or back down into the audience area. So these kind of unwanted reflections, these audible echoes that you get, you can reduce right down, and you could say we can really drive up the intelligibility of the sound in the space. So that's a really good use case there. So what parameters can we actually control within a coverage beam? So let's have a quick look at this. So we can look at the target level in terms of what we want to achieve, both within the audience area and the boundaries where we actually want to avoid. There's the level drop over distance, so how we distribute the energy. In a lot of instances, you'd obviously want a very uniform coverage, but there are certain times where you'd want all the energy to come off stage, and actually you want to reduce the sound down to the back of the audience area. Let's say there's a bar at the back of the audience area or something along those lines, or you just want to maximize the amount of energy you have coming off stage because you want the highest SPL you can achieve right in the front of the audience area. So you're able to do that and redistribute the energy there. We can do target frequency response. So this is kind of setting up a target curve. You can either have this maybe like just a flat response. You want the system to actually be completely flat, and we'll do that uniformly. So having that spectral uniformity right across the audience area, and they're sort of built into that optimization algorithm. Or you can kind of maybe for music reproduction, for instance, kind of have a haystack in the low frequency. And again, that's kind of built into the actual optimization algorithm to ensure that that is uniform across the entire space. Then we can adjust the target phase response as well. And this is kind of a trade-off between phase linearity and latency. So you can reduce the latency right down if you want to, certainly for live events, for instance. When you're working with bands or you're working with live performers, then you obviously want that latency as low as it possibly can be. But if you've got sort of canned content or pre-recorded content that you want the best possible phase linearity, then you can up that to a higher level and really improve that response and tighten up that sound. So you've got the option of how you do that. And then there's the air absorption compensation. So how much air absorption compensation do you allow for, over long distances, for instance? What are the atmospheric conditions that you're working with? What are the distances that you're throwing with? Can you put delay speakers in or not? Will actually influence the way that you actually use this air absorption compensation. And it's something that we do use in projects from time to time. So here we go. So coverage control. So we look at this kind of accurate precision and flexibility, these coverage zones that we're able to create. So what does the workflow look like for that? Is it really complex to do? Is there a lot of kind of number crunching that you have to do? Well, actually, no, it's a very, very simple process. So within our software, which is known as Holoplot Plan, we determine the audience area that you want. You can import that in through SketchUp if you want, so or a CAD file into SketchUp and bring that into our software. So you determine then that audience area, that zone you want to hit. You can determine which of the areas you actually want to avoid. You can even put sort of virtual boundaries in as well if you want to just assess against a plane, but it doesn't influence the actual the simulation. And we can go into more detail when we actually have a closer look at the software in terms of that. And then you obviously create your array. You then assign the array to the audience area that you want to hit, and then you optimize then the coverage. So there's kind of pre-processing that happens within the actual software to then optimize that for the area that you're trying to hit. And it really is quite sort of as simple as that in terms of the software and the way that works. So this is all within our system design software, which is referred to as Holoplot Plan, and there will be a more detailed look at that in future webinars. So what do we do next? Obviously, then we assess the results. And in this instance, what does that look like? So as we can see here, we can see the energy is very much constrained to this box that we see on the audience area here. So we've created this box within a wider audience area, and we can see we're reaching levels of around 95 to 100 dB within that box, and then you can see it steeply rolls off outside of that box. And we do this as part of the sort of the demonstration. We create these zones and we have people walk into them, both with speech and kind of music reproduction. And the roll off really is quite incredible as you walk in and out of these zones. So then another way that we can use this, we're actually able to create, multiples of these zones as well. Because I said we can create 4 of these beams from this single array in terms of these coverage beams. And each of these zones that we create here can have its own content, EQ, level, shape, and directivity. So it's possible to easily deliver multiple contents to kind of various locations, even with an open space. So, I mean, going back to the demo again, it's kind of one of those ones that really grabs people's attention, because we'll set up maybe 4 of these zones with only maybe a meter between them. And within these zones, we'll start off with just having some random sound effects within that. And people walk between them and they feel that they walked into very sort of separate environments, very different environments. You create a different soundscape and feel for each of those zones. And obviously a good use case for this maybe, if you have a museum exhibits in a very open space, or you have a kind of an immersive setup and you want to create these very sort of clear different audio zones, but within this open space that may be tied into a clear visual within that museum exhibit, then you can create these zones in front of the visual and make sure it ties in directly to that without spillover into the other zones. But the more practical use case that we often see is actually with speech and actually using it for translation. So sometimes we'll be able to split up maybe the audience into different zones if people want to have their own language within that zone, or again kind of in kind of a museum exhibit, for instance, where you want people to have different zones where they can hear their own language without having to be tied into wearing headphones to actually have the translation. Allows a more sort of shared experience and you don't feel quite as enclosed in. So a very interesting use case of this, and one that usually grabs people's attention. So then we've kind of looked at these zones, and then we can actually focus this down even further. And we, with the control that we have, we can actually sort of create this very, very focused content that goes down to kind of an individual experience then. And again, we set these up sometimes, with like 7 alongside each other, right next to each other, and people walk along these focused content and experience a different thing to the person standing right next to them. In terms of how precise you can be with this, it is then a function of the kind of the size of the array in terms of the frequencies that you can actually steer at. But when you understand the kind of constraints of those frequencies, you're able to design the sound around that and the frequency content of the sounds that you're using within those separate zones. So you still be able to walk between them and get these kind of really individual experiences. And this is great as kind of a layering up in an immersive venue, for instance, when you've got a soundscape going on around and you want to create what we sometimes refer to maybe as these Easter eggs within the venue. As you kind of walk through this space, all of a sudden you're hit with this sound that maybe your friend next to you isn't able to hear. Or sometimes if we want to grab people's attention, for instance, when they're walking into the venue, we can really isolate the sound down to one space, and then as they walk into the venue, there changes and it kind of bleeds then it right into another soundscape that you've created. So some really interesting use cases, and we're sort of providing these creative tools, and we're getting a lot of ideas back from creative sound designers who are finding different ways to use this functionality all of the time. So let's move on from there. So what does this look like then in terms of actual mapping? So we can see here in terms of the level we're able to achieve kind of within those focus zones, and then you can see how it so sharply drops off outside of those, creating these kind of very isolated beams there. You can see that it drifts a little bit in the vertical, and obviously that's to do with the angle of incidence of the actual array, and so the angle that it hits the floor at. There's always going to be a little bit of bleed out from there, but you can change that in terms of the position of the array to further optimize how that works. So now we move on to the Wavefield synthesis functionality, and this is probably a concept that you may not have come across before. And a lot of the time, we've only really seen sort of Wavefield synthesis in this kind of monopole setup with the speakers going all around in sort of universities, for instance, and you feel that the train kind of comes through the room at you, and you get this sense of sort of proximity. Well, this is a really interesting technique, and obviously one that works really well, but we haven't been able to get out into the mass market before because of the difficulty in deploying a system like this. And now we've managed to kind of harness kind of that sort of functionality and sort of bring it into the arrays that we use. So what is a virtual source? Well, a virtual source is an audio source rendered in free space, either in front or behind the array. The wavefront is synthesized to achieve the radiation pattern of, like, say, an acoustic source. You know, whether that be a bird's song, for instance, or someone speaking, or an acoustic instrument. The sound will radiate as it would do if that was actually there in that space. So giving a very kind of natural feel to that. And certainly when you place these behind the array, often you can place them and actually put different instruments as part of this and create this really natural sound stage then. And really sort of build that up, and it's and everyone within that audience, within that field of view, will localize that instrument at that position on the stage. So another really interesting technique that we use. So then we said you can kind of place these kind of behind the array, and then actually you can bring these virtual sources out beyond the array and in front of the array here. So how does that work? Well, as you can see here, you can see how the wavefront then converges down. So this concave wavefront converges down to a single point, creating this very, very tightly focused sound bubble almost. And it really does feel like a bubble when you experience this. As you walk into it, you know, you can optimize it to head level. You can duck down out of this, and you know, it's very, very precise in terms of the way that works. And then the actual source then will radiate like a point source from that space. So it will diverge out from that space then. So the wavefront converges down, then diverges out. And again, you can sort of optimize the way that you set up the array to get the best experience from this. And then another way that we actually use this, which becomes really interesting, is we actually use it to create reflections. So we use the architecture of the space to our advantage. You know, a lot of the time what we're trying to do is keep the energy off the walls and you know, reduce these reflections, which is something I talked about earlier in this. Well, now we're actually bringing them into play. And why do we do this? Well, we can use these virtual sources and create reflections off walls that are very, very precise. And it almost will work like a virtual loudspeaker that's kind of mounted onto these walls. And anyone who's kind of come to the demo will have experienced this in terms of it feels like there is these sort of virtual loudspeakers. You can create this sort of 5.1 or 7.1 mix, but without actually having to hang these loudspeakers, without having to have this distributed system, which sometimes, you know, architecturally, depending on the age of the building and things, it's very difficult to install a distributed system. It's costly, it takes a lot of time, and this is a way of kind of bringing in this kind of layer of immersion, this kind of feeling of envelopment and the surround sound aspect to your sound design, all from this single point, from this single array, and kind of it all radiating from there. It's really interesting in the demos sometimes because people don't believe that actually what we're doing is reflecting off the walls, and you'll find that they walk in and they'll start looking behind and looking to see if we've actually integrated loudspeakers in there, because depending on the reflective surface of the wall, you know, the absorption coefficient is obviously important in terms of how it reflects the sound back. You can get a really, really good reflection off there, a broadband reflection. That you know, really does sort of fool people into thinking that there is a real loudspeaker placed there. So in terms of being able to localize this sound, I think we talk about what we call a field of view. Now, field of view, so we have this listening area where we're precisely able to localize these virtual sources. If you go outside of that kind of field of view, then that localization breaks down. But within that listening area, then you're able to very, very clearly pinpoint the sort of localization to that with a really high resolution when using Wavefield synthesis. And then same thing kind of happens then when you bring the actual virtual source out in front of the array, and you can see kind of how that changes, how that sort of slightly changes that kind of listening area and where you're able to perceive that. So yeah, I mean, this will result initially in sort of a concave wavefront converging to a single point in space, as we talked about, and then beyond this, the point that it will diverge out again. And we can see how that works on the diagram there. So that's kind of virtual sources, and that's how that works. And I think it's one thing that you kind of have to really experience for yourself. You kind of have to come to the demos. You kind of have to get a feel for how that works. It feels quite abstract when you first talk about that, but then really understanding it, it's really, really interesting, and it really brings another dimension to the way that you design sound. So then the key takeaways from today, really, I think I've sort of raced through quite a few of those slides, and I just want to kind of sort of go over a quick summary of what we've talked about there. So the Holoplot X1 system, you know, what does it deliver really? What problems does it solve? What's it doing? So directivity control, we kicked off with that in terms of this quest for directivity control and how we achieve that. And we've seen the kind of evolution of the loudspeakers as it moves through that, and us now bringing in the matrix array, the ability to control in the vertical and the horizontal, this precision that we now have to be able to focus the energy into the audience areas, to create this homogeneous coverage across the audience areas and achieve this spectral uniformity across these areas is something that's not been achievable before. And you really do drive up the intelligibility of the sound within your venue. So as we just talked about, this homogeneity of the sound coverage, this spectral uniformity across the audience area, really these optimization algorithms are really like nothing we've seen before. So improved intelligibility, especially in the acoustically difficult environments, and that's kind of worth talking about because a lot of the design that I started doing actually back when I was as an acoustic consultant, as a PAVA engineer, was in acoustically difficult or hostile environments like train stations, like sort of major transport hubs, whether that be airports, well, these places where you get very loud background noise and very high reverberation. Using these features that we've looked at so far in kind of auditoriums, but actually using these features in venues like that and being able to control the sound, you can really drive up the intelligibility in spaces like that too. So, and then there's this separation of sound zones in an open plan space, and I think this is a really important one. I think this is one that has very sort of practical applications, this ability to create these different acoustic zones within this space, be able to move between different zones within an open space and have a very different experience as you move through those, without having to have a complete sort of distributed system to be able to do that, doing it from a single point. And then this amazing precision that we've seen of tight and focused sound beams, this being able to create these real sort of individual experiences, the ability to kind of have this sound down to kind of a single listening experience is really, really interesting and really does kind of add an extra tool kind of into your sort of creative palette, I suppose. And then we talk about these tools. So the previously unavailable creative tools, a lot of these tools that we talked about, conventional systems just cannot do, and Holoplot system brings these kind of new tools now, these new creative tools to the industry that have not been seen before, and certainly bringing all of this functionality together in one system. So not only do we have all these features and functions, actually it works as a conventional system too, and is a very, very good sounding system. And that's something that you'll find by experiencing the demo, coming to some of our venues, seeing how the Holoplot system works, and really kind of getting involved in the mission. So yeah, there's an information package available here with the code. This is all about joining the mission now, really understanding what we're doing that is different and really getting on board with the Holoplot X1 series.